are difficult, very difficult, especially when the dimension is large. So in cross layer optimization, different models were proposed by many researchers and Madame Tang, Yu. Here we consider a cross-layer design problem to allocate time and power resource to links in an interference limited wireless network. For this problem, people work with a mixed 0-1 problem and at the present time an efficient scaling algorithm has not been found. That is why we propose approach based on DC programming and DCA. We present now the mathematical model. And not use actually. That is a notation and notation. We are the no set, a set of unidirectional link, traffic drawing entirely partitioned into fixed length frame, which is divided into J and I slots. The maximum function power. And here we are T is a continuous variable, while S and J is a binary variable, 0 and 1. So we have to maximize network lifetime with a set of constraints. There are non-convex constraints because this term contains the product of the variable, binary variable and the continuous variable T. And some constraints which represent the traffic law some condition on the right at each node, and of course the flow conservation, that is common for network problem, and some condition. We continue with the last constraint. Mathematically formulated, this problem takes the form. We have maximize the lifetime, network lifetime, with a set of bilinear constraints, and the rest are the linear constraints, and continuous variable and binary variable. Of course, this problem is difficult, it's a non-convex problem, because of the binary variable, and also by the bilinear constraint. Bilinear, non-convex. Variable, binary variable, also that introduce non-convex constraint. So
the question is how to solve efficiently this problem. Of course, we should find efficient, but not only efficient, but also scale and quick. It belongs to the class of problem that people call the challenging problem in wireless network problem. So now we will present the reformulation of this problem and also the algorithm for solving this problem. The algorithm will be based on the DC programming and this data. My colleague, Professor Dr. I've just present to you. Instead of maximize T, we minimize Q over T. And so we can transform the bilinear constraint into linear constraint. Very simple. For the 0, 1 constraint. Okay. Okay. So we have to minimize Q under linear constraint, and the rest, the remaining constraint, all are linear with, of course, the binary variable. To apply DC programming in DCR, reformulate this problem into the form of minimizing DC function different two convex function over convex my colleague. So, how to do? Okay, we use. I think that people certain know that we can penalize the binary variable constraint. This time, 5 minutes. So, excuse me. So we have to. We have the problem difficult. The approach used by ACIIDS to solve we will present computational experiment compared to those given by ACIIDS. ACIIDS solve this problem in the combinatorial approach. For us, we solve this problem in continuous approach. Okay? Transform into a continuous domain using penalty technique in DC programming. I start you with the description of DC. Okay, so the spirit of DC programming is to replace a DC function, a DC program that is minimize a DC function over a convex set by a sequence of convex programs. So each iteration, we have to solve this problem. Okay, of course, because in general, and that also the objective, what to do when people would like to apply DCA. The first thing to do is what is the DC composition with the convenable, very traceable to the structure specific structure of the DC program. Okay, in order, for example, to have the 2-second escape evacuate explicitly obtained. Okay, if it's not the case, we have to solve this problem. Okay, how to apply this transform into continuous basic DC decomposition. So you can use this theorem, penalty technique, that is the penalty technique in DC programming. What is say? You say that if you use, if you have a concave constraint, if you can express the problem with the concave constraint, then the two problems, the original problem and the penalized problem, are equivalent in the following sense. They have the same optimal value and the same optimal solution set. Okay, and so it's, and in this case, we can only solve the penalized problem in the continuous form. So we will propose this transformation. We can use the function concave. We take this form, the sum of 9 S and G and more and G. The other penalty function, but the function will give will lead to a polyhedral DC program. For this, DCR enjoy some important element property in practice. And so in this case, we have two problems. We can write the original problem in this form and apply the penalty result. Finally, we have the two decomposition, explicit, and can apply the DCA. We can observe that the computation, we can, for this case, we can also solve a program, a linear program at each station. Okay, pass. So now, finally, we present some computational reason. This table represents computational reason compared with the simplex algorithm. Simplex, the most powerful commercial algorithm. Okay. Then I think we should read only the last two columns. Here, that is the data. We have the number of computed variables, the number of binary variables, and the number of constraints. The value given by algorithm DCA, the value given by C++, and the first thing to look at is CPU time. Okay, and also the value. C+ is a global algorithm. Okay, and DCA is a local algorithm. Okay, but I will say something just before ending my talk. Okay. The value that is not quite different, but the CPU time. And here, CPU time of C++. That is the DCI is scalar, efficient. We give approximate solution, approximate global solution, but with time, with the CPU time. Very important. Okay, and here. So we propose DCA script with a sandwich problem and compare the algorithm with those of C++. The algorithm give a good, very good optimal solution, but with a CPU time very small. And really it's scalar. It will be very useful for researchers and practitioners who would like to solve mixed integer problem in the class case. I will finish my talk. And I would like to say, for non-convex program, finding a global solution is a quest of holy grail. And people agree that we should instead find a local, efficient scalar for solving real-world problems. It's a lot of work. I would like to say to people who have the non-convex program to solve. Thank you very much.